Well, hey everyone, welcome back to Quick Soil Mechanics Lessons with Brian. We are continuing with liquefaction, simply explained in 12 acts. Getting close to 12 acts now. Act 9, cyclic liquefaction in tau epsilon space. Let's just have a little bit of a review. So here we have our triaxial test sample on the lower left-hand side with the orientation of the principal stresses. Of course, sigma 2 and sigma 3 are equal in a triaxial test sample. And here we have a Mohr circle in total stress space showing sigma 1 and sigma 3. And we also have an equivalent effective stress friction, Mohr circle. And the difference between those two, of course, is pore pressure. And because we have both effective and total stress, we need to add our effective stress friction angle in there. So if we take our sample that's initially at atmospheric pressure and we put it under confining pressure to whatever we wish, of course that's on the x-axis because sigma 1, 2, and 3 are all equal. So it's a hydrostatic pressure applied by the water, and it's equal all around pore pressure. So let's take that and start to load the sample. So if we look at MIT space, we have a total stress Mohr circle and an equivalent effective stress Mohr circle. We keep loading that up and loading it up, and you can see the black circles are following a pattern with sigma 3 remaining the same and sigma 1 is increasing, so the vertical stress is increasing. The equivalent effective stress Mohr circle is just doing whatever it wants based on the pore pressure that's generated. So we keep loading and loading and loading until we hit the friction angle and the total stress is finished, and now the effective stress is finished. Now in MIT space, we can connect the top of those circles by plotting a point at the top, then a straight line goes through there. And with effective stress, we can do the same thing. The top of the circles, put a line to it, and it just followed whatever pore pressure it generated to get to that line. And a much simpler way to look at it is to take away all those circles because there's an infinite number of circles involved. And then we can take off those points. So those two stress paths are the total stress path and the effective stress path. And those are really important to look at, much more meaningful than a bunch of Mohr circles, especially just the final ones that are on the envelope. You need to know how they got there and what the pore pressures were. So let's change the topic a little bit and look at how epsilon space here. So this is a stress strain curve. And let's make a little space at the bottom because we want to have compression as well as extension. And let's make a little space on the left-hand side because we can also have negative strain in the other direction. So if we have a sample in a triaxial cell, we can do an initial loading on it, and you can see here it's in elastic space. So we've just loaded it, that's all we've done. And if we want, and we could also unload that sample. And unloading, it goes right back down to that origin. It's still in elastic space, and there hasn't been any hysteresis like we saw in a previous act. So it's just come back down to that origin. We've loaded it and unloaded it. Now we've loaded and unloaded that in compression. We could also do the same thing in extension. And if we do that, we have a stress reversal. So we've gone from a positive strain to a negative strain. We've gone from compression to extension. There's been a stress reversal. So it's still acting elastically. It still went up and down on the same straight line, ended up at the origin, so there hasn't been any plastic deformation to that sample at all. Okay, so if we look at a cyclic triaxial test, let's see what happens there. So we have that initial stiffness, and we repeat that, and we number of cycles on here. Pretty soon it loses that stiffness. Then we'll get these long loopy curves where we've lost all of that initial stiffness, and the sample is actually liquefied under cyclic triaxial conditions. So for now, we will stop right there. That's a lot of information, and we will continue in the next act.